Hello world, it's Calcutron here with part 3 of our snake program tutorial. In this episode, we're going to be finishing up our snake game, finally. Now, it may seem like we're already done. We have most of the game mechanics finished. There are just two more things we need to add, and that is making it so that our snake can die, so we can finish the game, and then implementing a high score system. So let's start with making our snake so that when it runs over itself, the game ends. So just to recap, let's run this program and take a look at the behavior. So we move our snake around, and each time we find a piece of food, we eat it, and our snake grows in length. And we were able to implement this by having a matrix, an 8 by 16 matrix that is filled with numbers, and those numbers represent 1, 2, 3, or 4, represent whether or not the snake is moving up, right, left, and down at that position. And so we're able to keep track of just the head and the tail and the positions of those things in X, Y, S, and T. And by just keeping track of the head and the tail and using this matrix of directions, we're able to know where our snake is flowing. So if we look at our matrix A, it's sort of like a flow map, and we can put ourselves anywhere in here. Let's say we start here with this 2, and we know 2 means go up, so we can follow the flow of this and go up, and then 3 means right, so we go to the right, we go to the right, and we keep going to the right, okay, and here we finally find a 4, and the 4 tells us to go down, and then to the right, and then up, and then to the left, and the left, and the left. So we can follow this around, and that's how the tail keeps moving around this. However, you can see it gets pretty cluttered after a while. It just looks like junk. We can't really gain much information from this. But you see here on the screen we have a couple places that are 0. Like down here's a 0. Here we have a couple zeros in the middle of the screen. And what those zeros really mean is the snake has not been to this location yet, because otherwise it would be one of the directions. So we can tell where the snake hasn't been by the fact that there's a 0 there. Now what we'd like to know is where is the snake right now? Or we'd like to test a point, the next point the snake is moving to. And if that point is already occupied by snake, then we want to end the game. We want to call that a game over. And so what we're going to do is, in order to make this not cluttered, just like we've done on the screen, we want to erase where the tail is, where it's been, and then we'll know where our snake has gone and where it has not gone. Or not where it has gone, where it is currently. So let's do that. It should be fairly simple to implement this. We just want to go down here a little further. So right here, where we access the current location in the snake, we can now that we know it, we can forget about the previous location, or forget about that number and erase the snake ever being there. So what we're going to do is right here, and at the same time we're clearing out that space, we're going to store a 0 into matrix A at t comma s. Now if we run this, we can see our snake is moving around, and we're eating food, and we're growing, so that clearly didn't break anything. And now if we run over ourselves, wait, we haven't done that yet. So now if we exit this and we look at our matrix A, everything is a 0 because it's getting cleaned up after itself, except for these places right here. And you'll remember at the very end the snake was all moving left, and this reflects that, and it was 4 or 5 long. And we can tell, oh, the tail must be at this position 715 because it's the last point in the snake and it's yet to be erased. And if we check our variables t and s, those are the same positions that we were seeing in the matrix. So Now we just need to use this information and detect when the new head of our snake is in a location that is already occupied. And we're going to do that by modifying our termination condition for our main game loop. And that is right here. It's that repeat until k equals 45. Now we want to keep this repeat until k equals 45. We want to be able to press the clear button in order to exit this loop. But we want to add the condition that if we run over ourselves, we also terminate the loop. So we're going to do that by doing an OR. So we're going to repeat until k is 45, so the user quits, or they lose. And we'll track that by if matrix A at y comma x, this is the position of the head, yes, or that does not equal 0. So once this is something non-zero, meaning a part of the snake, then we can finish our repeat loop. And we can actually optimize 3 bytes off this. We don't need not equals 0, and it's a good exercise to think about drawing a truth table. If you know about truth tables, draw a truth table for x equals true, and see if it changes the value of x at all. Spoiler alert, it doesn't, and it's the same for x does not equal false. It's the same as just putting x. So if we run this now, we're going to have to play a little bit until we get our snake long enough to demonstrate, but I think this is a good length. We can see I just ran into my tail and it terminated the program. So that is a really good start. Now the next thing we're going to do is add a high score system. So you might say if you don't care about high scores, you could be done. Your snake program could be finished and you can go ahead and turn this video off right now. But if you want to implement a high score system, and I highly recommend this, it's a lot of fun to track your high score, I'm going to recommend using this method. So we're going to have a list. We're going to use list 6 for this, and that list is going to contain our top 5 high scores. So let's say hypothetically our high score is 30, and then our next high score is 25, and then maybe our next high score is 24, and our next one is 24, and then maybe our next high score is 22. So we're going to store our high scores in a list, and then when we want a new high score, we're going to have to sort that new high score into this list wherever it belongs. So let's say we scored a 27. We want that 27 to go right here and bump off this 22. And the strategy we're going to use for that is we're going to have an extra space in our list, just a blank space in the 6th slot. So I should have said this before, we're only keeping track of the top 5 high scores. So we're going to have sort of a wildcard spot here in element 6. And in element 6, we're going to put our new high score, or our new score. So let's say we score a 27, we're going to put a 27 here. And then what we're going to do is we're going to sort the list. So let's store this into list 6. I think I'm going to use list 6 for my high score list, but you could also use a list with a custom name. You could call this list HS for high score, but I'm going to use list 6. Nope, list 6. And we can see we have our list of high scores, and then we have our 27, which is our newest score. And then we sort, let's not sort, we sort this in descending order. And what we get is the same list, except the top 5 are now our new top 5 high scores. And then this 22 has been put in slot 6, and it's no longer a high score. And so let's say instead of getting a new high score, we get something that is not a high score, like we score 15. Then our list is going to look like this. And when we sort it, its order isn't going to change at all, and we still only look at the top 5 when we're displaying the high score. So another thing I like to keep track of in my high score system is my average score. I find it fun to try to improve my average so that even if I'm not getting new high scores every game, I'm still affecting a number in that high score menu, and I can strive to improve my average. And so we could use another list to store information about how to compute our average, but we're going to be a little sneaky, I guess, and we're going to put that information in list 6 as well. So we're going to put in well, first off, we need two numbers in order to compute the average. We need the number of games played, and then we need the total score of all those games, and then we compute the average as the total score divided by the number of games. The first thing we're going to store is the number of games. So let's say I played 10 games to get these high scores. And then we're going to put the total score over all those games. So maybe my total score over all those games is 200. So this way, we can use these two numbers to compute our average score. It would be 20, 200 divided by 10. But now we have a problem. If we try to sort this in descending order, we're going to get this 200, our total score, bubbling up to the front every time. And we're going to get this 10, our number of games played, going down to the bottom. But let's say next time we played 25 games and our total score was 500, then our 25 would get sorted into the middle of this list, and we don't want that. So we're going to use a little trick to avoid that, and we're going to store these as the negative version of the number of games played and the negative version of the high score. So that way, we'll be storing this as a negative 10 and this as a negative 200, and we can still compute the average by just dividing this negative 200 by negative 10. It will still be 20 because a negative divided by a negative is a positive. And this will always sort into this order because we can never have a negative score. So this will always be lower than those, and our total score will always be higher, and in this case the negative of that will always be lower than our number of games because we can't have a score less than or equal to 1. So this strategy should work out good. I just realized we don't know how to get our score though. So first let's figure out how to get our score, and then we can move on to implementing a high score using this system with list 6. But even before that, I'm going to clear out list 6. So I'm going to store 8 into the dimension of list 6, and then I'm going to fill list 6 with zeros. Fill zeros into list 6. Alright, so now we can implement tracking the score, which is fairly easy. We start out with a snake of size 2, and so let's store our length into a variable L. So 2 stored in L, and then if we go down, we just need to update L every time the snake grows. So let's find where we handle eating food. I believe it's right here. So on this line, we want to come up with a new position of the food. That's why we're using this randint. And then we also want to increment the size of our snake. So L plus 1 stored in L. So now we have a larger snake, and then we can go down to the bottom, and here we're clearing the home screen after the end of our program, and we're going to output at 1, 8 the score L, and I forgot before that I want to display. That's why I chose 1, 8. So it's row 1, column 8, and I did that because we want to display that this is the score. We want to put a label next to this. Oop, this is the score. And I believe that puts us in column 8. We have 1, 2, 3, 4, 5, 6, 7, and then we'd want our score to be right here. So that is 8. So hopefully if we run this, then we should have the score displayed as soon as we lose. So I think our snake has length maybe 8 right now. Let's see. Oh, so our snake had length 9, and because the screen is length or height 8, we can't fit the entire snake vertically. So I knew if I went up, I could make myself run into myself. So there we have a score of 9, and so now we need to do that thing I was talking about with if our score is 30, 25, 24, 24, 22, whatever. Those, it's not necessary that it is those numbers, that's just an example. We want to put our new score into position 6, so after our 5 high scores, and then resort it. So our score would be 9, and we would resort it, and it wouldn't change anything in this instance. So let's go back in here and go to the very bottom and do just that. So we want to do L stored into list 6 at index 6, and then we want to sort, that's not sort, sort descending on list 6. So list 6 has been modified by this sort descending function, and then now we want to display our high scores. So we're going to go for A. A will be our index into our list. From 1 to 5, we want to get the top 5, and then we want to output. First thing we want to output is what number high score is this? Is this our number 1 high score? Is this our number 4 high score? So we're going to output A, and we're going to output that in row A plus 2, and then in column 1. So we're doing row A plus 2 so that it starts in row 3 and then it goes to row 7. So we'll have the score, and then right now it'll be a blank space, and then we'll have our top 5 high scores, and then we have space for one more thing to put at the bottom, and that's where we'll put our average. So this is the number of the score, and then we're going to output at A plus 2, same row, and then in the third column we want to output the actual score, which is list 6 at A. Hopefully that makes sense. That's a fairly basic use of outputs and for loops. And then, yeah, let's try this out. Let's see our high score list in action. For the first one, it's not going to be very exciting because whatever we score is going to get sorted to the front of the list. But we can at least get a high score. So our high score is 7, and we can see the rest of our scores are 0. So the next thing is to do the average. So let's go down to the bottom. Oh, wait, yes, this is correct. So instead of incrementing our number of games played, we want to decrement it because it is actually the negative of our number of games played. So that is list 6 at 7 minus 1 stored into list 6 at 7. And then we want to decrement our total score, or not decrement, but we want to decrease our total score by the number of games, or sorry, by the score we just played. So that's the same thing as adding our new score to our total, except that we're doing everything negative, so we're subtracting. So that's list 6 at 8 minus L for our current score, L, stored into list 6 at 8. And then now what we want to do is we want to display our average. So I'm going to output a label. We'll call this AVG, colon, and then we want to, we will need to give this a position. So this is row 8, column 1. And then we want to, on the next line, output in row 8, column 6, I believe. 6, yep. Column 6, we want to output our average score, which is list 6 at 8 divided by, so that's our total, divided by our number of data points. Total divided by a number. So that's list 6 at 7. And there's just one thing that I am going to change about mine that you don't have to, and that is I'm going to truncate this. Actually, it's not truncating. I'm going to round this down to the 100th place because I think it looks nicer when you only have small numbers, or small width-wise numbers, small number of digits, and when you get a fraction like this with a recurring decimal, it's gonna output an average that has a lot of numbers in it. I think it just looks nicer if you force your average to be only 2 digits of precision past the decimal. So we're going to use the round function for that. I don't think I've talked about that before in any of my videos. Oh, I must not be very good at the round function because I just passed it anyways. But I don't talk about this very much because I don't find it useful most of the time, but in this case, we want to round to 2 digits of precision, and there's not many ways to do this that are better. So that will output our average, and it will label it as such, and it will round it down to the hundredths place. That's what this 2 is. It's going 2 digits past the decimal. So now what we want to do is I'm just going to add one extra piece of something that I think makes it look nicer, and that is I want to know if it is a high score. So if we can test if it's a high score by seeing if our new score is greater than the worst high score so far. So we can test if L is greater than list 6 at 5. That's the worst high score. Then, and then we want an else and an end. I like to know when it's a high score and when it's not a high score. So in this case, I want to display new high score. And that's exciting to get a new high score, so we'll put an exclamation point on, and you can get an exclamation point by going to math and then probability, and then it's this factorial. And then otherwise, I just want to tell the user that the following table is the high score table. So I'm going to label this as the high score table. I think that is probably it. Oh, I put that in kind of a weird place. I'm just going to move this outputting the score before outputting the high score. It'll all happen so fast it won't matter, but logically I think it makes more sense to do it like this. So we're putting this in row 1, column 8, outputting L. Alright, so if we run this now, I guess this time I'll focus and I'll try to get a real high score. Oh, it was not a high score. So I got another 7, and that is kind of unfortunate because 7 is not what I was... It doesn't allow us to show off how the average is working, but we can take a look at list 6 and verify we have played... Oh, this makes sense. We have played one game with a score of 7, and it hasn't done an average of our last game because we hadn't implemented that yet. So let's go ahead and clean that up, because now our high score list is not going to be the same as our average list. So we'll store a 0 into list 6 at 2, and that ought to clean up that issue. It's only because we were playing it before it had finished that error happened. Another thing I noticed, and you probably did too, was that a done message popped up. And we can remove that done message by using this trick. We put just a single quotation mark on the last line of our file. And by doing that, it's storing this expression. A single quotation mark is actually an expression when put on a line by itself. And we're storing the result of that expression into the answer variable. And I'm sure you've used the answer variable when you're doing math. It's very useful. But it can also help us when we're trying to get rid of the done message, because if the last line of your program is an expression, it will store that, or it will use the result of that expression as your done message. Speaking of using the answer variable, we can actually optimize this in another little way, and that is whenever we store into a variable or into a list, it also stores that into the answer variable. So on this line, we store a new value of the total score into list 6 at 8, and then we can use that down here and optimize away a few bytes by doing answer instead of re-accessing the list. So that'll save us a byte or two. Now we can exit out of this and play our snake game, and hopefully all went well, this will work correctly. So I guess this is the end of the episode. So no reason for me to lose on purpose. I can play a long snake game. Oh, never mind that. So my average score is 8.5. Yes, that's correct. And we do not have a done message. So we have an awesome snake game with a really cool high score system that allows us to see our average. And I'm pretty sure it works, although we'd have to do a little bit more extensive testing to make sure it does. But anyways, let's just quickly take a look at the size of this program. This is 493 bytes. That's strange. My first implementation of this was 499, so I must have optimized something since then. Either that, or I forgot to include something, and this actually doesn't work. Let's hope it's the former and not the latter. But I think this is a fairly impressive small size for a snake program for how well it performs. And if I ever do deeper computer science topics, we can talk about the algorithms and data structures used in this program and how there are other methods that may do better on size and worse on speed. And maybe I'll come out with another video about that. But for this, I tried to optimize it for speed, and hopefully it runs fairly fast on your calculator. And I think the size of the program was fairly good, but I definitely challenge you to optimize this program. I am 100% sure this can be optimized to be fewer bytes without changing the semantics of the program. And so a great challenge if you're learning TI Basic or if you're a veteran TI Basic programmer is to find other people's programs and optimize them. And that'll really help you in your own optimization efforts. So please leave a comment with an optimization you'd like to add to this program. If you have any other questions or comments, also leave those below. And I hope you enjoyed. Bye-bye.